talk about engineering geology and geotechnical engineering, something hopefully everybody's at least heard of once or twice. So what do we do in the engineering geology and geotechnical engineering branch? You know, we provide technical support to engineering, operations, and maintenance, but up above there, these are the topics that we're charged with, which is soil, rock, and groundwater. So anywhere that soil, rock, and groundwater are going to affect a site or affect the workings of ODOT, then we're basically asked to intercede and to be the technical representative for those issues. We have a subdiscipline, which is hazmat, hazardous materials. Sean Rapp, who's in the back of the room, is our leader on that. So we do hazardous materials assessments, predominantly lead paint or paint surfaces, asbestos that's involved in construction. So we go out and we assess that to find out if it's going to be in the way of a project that we're going to be doing. We do soil and groundwater contamination cleanup. A lot of times that impacts the site. Groundwater is impacted because of a gas station that fronts a highway, or there's been some sort of a fuel release. So we do the cleanups with those. Sometimes it's a tanker truck accident. Waste management. We generate a fair bit of waste. We demolish structures that have lead paint and asbestos on it. We dig up soil that's impacted by petroleum. We have all sorts of waste that we generate, and as we generate that, then we have to manage that and make sure that it's distributed and placed in a place that's legal under state law. And finally, we do site-specific and corridor assessments. So the intent is to be proactive to figure out, well, what contamination could be present before we find out in the middle of a construction project that it's there. So we do various site assessments of corridors or areas where we're going to be working or where perhaps we would do a right-of-way purchase. So one of the big issues, and one that I think a lot of people don't quite understand in the geotechnical engineering, engineering geology discipline, is that we have two very distinct professions that practice within this. So there's engineering geology, which is a very specialized part of geology that is licensed to be able to be involved in engineering works. And that word engineering in there is a little confusing. Sometimes folks don't quite get that engineering geologists are not engineers. Geotechnical engineering is a specialized branch of civil engineering that predominantly deals with soil and groundwater. And because of the phrase geotechnical in there, sometimes folks are a little bit lost on the idea that we're not geologists. So I'm a geotechnical engineer, I'm not a geologist, and I try and not practice as a geologist. Curran, as an example, is our senior engineering geologist. He's not an engineer, and he endeavors not to practice engineering. There is, if you think of your classic Venn diagrams, there's that overlap in there where basically some of the work we do involves either of us. All of it should involve both of us, but some involves either of us. So the reason I think this slide is really crucial as you go forward and work within ODOT is that if you have a question for somebody on our side of the fence, the fence is bad, but in our group, and you ask somebody, don't be shocked if they go, you know what, that's actually an engineering question. I'm a geologist, let me have so-and-so take care of that. Or vice versa. Oh, you know what, that's really geology. Let me get so-and-so involved. If they just blow you off, that's different. But ideally, they should tell you who that person is. But honestly, don't be shocked. They're not being a pain in the hiney. We really do try and not do each other's jobs. And so honestly, it's not inherent upon you working for ODOT to know exactly what those differences are and where those Venn diagram overlays are. That's our job. We need to know that, and we need to be helpful. And sometimes the most helpful way we can be is for me to say, let me get Curran on the line. He's really the person you need to talk to. So honestly, of all the slides, this may be the one that actually might impact your life the most, just in terms of, being kind of mellow about the fact that you get what may seem like a blow off, but isn't really. So what are the main technical things that we're resources for? So site grading, anytime we're picking up soil in one place and putting it in another in order to create a roadway or to fix something, that's ours. Foundation support, whether it's deep foundations like piles and piers or spread footings, that's ours. Seismic ground shaking. So taking that earthquake, predicting the earthquake, running it up through the site and saying what's it going to do to the structure, to the bridge, to the roadway, that's on us. Landslides and rockfall, big part of what we do, very much driven by our engineering geologists with geotechnical engineers involved as well. And finally, material sources. There are many parts of the state where commercial quarries are not readily available. When those commercial quarries aren't readily available, we, ODOT, need to develop sources, and that's predominantly on the east side of the Cascades, but there are also locations here in the west, and so we have a program that works on developing and permitting those sources. So what kind of services do we do within those technical ranges? One of the big ones is addressing issues in the field. Something comes up in the field, whether it's a landslide or whether it's a problem with construction, then we're there to sort of counsel and say, well, here's how we can fix this. We work with maintenance and contractors on that all the time. A lot of short-term needs where maintenance doesn't have the specific experience and we do. We develop written recommendations for constructed works. That's our main deliverable, is a geotechnical report, and it says, okay, here's the soils that are out there and here's the problems you're going to have when you go to build this, and here's the design parameters you need in designing this. So that's our main deliverable, and that's the deliverable that a lot of you are going to be seeing come across your desk if you haven't already seen those. We have statewide technical expertise on all of those subjects located in headquarters, Curran, myself, Susan Ortiz, Sophie Brown, et cetera. Project delivery, consultant scope of work. So we write scopes of work, statements of work that then go into consultant selection packages. We do training, fair bit of in-house training as well as bringing in outside folks to train our staff. We're responsible in headquarters for guidance, for the standard drawings, the policies, and the manuals. And then finally, we do some asset management. We're actually going out and looking at all of the unstable slopes that could impact lifeline routes. So after a major earthquake, we expect a certain number of landslides. We're trying to figure out where those are, prioritize their repair. And then finally, retaining walls. We do the same thing. Look at that as a programmatic way, as a series of assets so that we stay on top of retaining wall maintenance and potential failures. How do we do this? We start off with subsurface explorations, a couple of classic shots here. One is drilling off a barge. We're in the bridge business. And so frequently we need to know what is the subsurface next to an existing abutment or where we want to, or a bent, or where we're going to put a bent. And as much as it's nice when bridges span across an entire river, we have lots of big rivers, that doesn't work that often. So we want to drill as closely as possible. So ODOT probably does as much barge drilling as any organization in the state of Oregon. And then you have sort of conventional land-based explorations that you see here next to that. In addition to that, we have various the probes and test equipment that can be pushed into the ground to measure the soil as well. So then we collect samples from our drilling and we bring those in, and they go to a ODOT materials lab. And we have a very full-service lab that can do just about any test that you want to do. And they do excellent work for us, and they're located in Salem over by the airport with the materials folks, and they do excellent work for us. We do have some specialty tests. There are some seismic tests that we do where we shake the soil and see if it wants to fall apart in an earthquake under a liquefaction type scenario. We send those to Oregon State, or we send those to a series of high-end commercial labs that are available to us. The testing is necessary in order to sort of hand the project off from the geologists who characterize the site and figure out the soil and the rock, and the engineers who do the actual analysis. So the more numbers we can have, the more focused and appropriate our analysis can be. So the engineers need this laboratory data, in order to be able to adequately design projects. So the testing is essential for those design parameters, and a lot of times you can look at soil and not know that it has the problems that it has. And liquefaction, the loss of soil strength during an earthquake, is a classic example. There's no visual test for liquefaction. You really do need to sort of test it in the laboratory. Just gives you an idea. Some soil samples is from the ODOT Flickr page. This is just from one stretch of Newburgh to Dundee. So you can see that, even though all of these soils are kind of in the same family, silts and clays, there's a huge variety on a given project. And we have to sample and know and understand all of these soils and kind of put that together. It's a cool photo, whoever took it. When I talk about grading and excavation, here's a nice photo that kind of gives you an idea. In the background, you can see that they're building an embankment. In the foreground, you have this large excavator who's helping to dig this soil. It's a little bit on the rocky side. And so we're picking it up from this place, we're taking it to the other place, and we're going to compact it in place. We're the ones who basically say, well, here's how you're going to do it. Here's the problems you're going to have with that. Is it going to be on the wet side? Is it going to be dry? How's that going to work, and how are you going to accomplish that? Rockfall and mitigation is pretty huge for us. So you can kind of see in the first photo that there's a rock that fell on the ground. Well, I'd say you can see that, except there's something over the top of it. But a big boulder fell down on the road. The second photo is what we did about that. So the photo here on the lower right, you can see that they're draping basically what looks like chain link. It's a much stronger version of chain link over that. It doesn't stop the rocks from falling. What it does is it takes the energy out of them and transfers them to the bottom of the slope so that theoretically they're not bounding out on there. In addition to that, you see these two guys standing here. That's a job called scaling. And their job is to find the loose rocks that are already there and pry them off and make them fall. And it is the dumbest job in the world. If you ever think you want to be a rock scaler, you don't. And it's super cool to stand across the road, and I mean across the road, and watch these guys work. But they're up there with pry bars, and their safety equipment consists of a rope and a helmet. I'm not sure exactly what that helps, but anyway, we couldn't do our jobs without scalers. Thank goodness they exist. But it's a questionable job for anybody to undertake. Certainly a young person's job. Landslides, absolutely huge for us. Landslides can do a number of things. In the upper left photo, you're going to see a landslide that came down and buried the roadway. So that's a very common mechanism where we've made a cut into the hillside or there's something unstable above and it buries the roadway. So we got to go in, dig that out, put something back where that was, figure out a replacement for that. That's on us. On the right-hand side, you'll see a slide that wants to take the roadway away. Usually that's because we built a fill on the outside of a hillside. The fill isn't particularly strong or the hillside isn't strong, so it wants to slide away. So you can see that sag point there. Well, that's the roadway going away. The lower left, that's Huskaneden, and that's a landslide that is a half a mile up the hill and a quarter mile down the hill into the ocean. And our road is just the tiniest little ribbon of asphalt through the middle of what is an immense regional slide. And that's actually why Curran is not here, as he's on a reconnaissance of Huskaneden. This photo is just from last February. We've already built a ribbon of asphalt back across that. It'll be our fourth or something that we built across that. And the next time we have a big rain event like we did this last fall, then we're going to build another one of those. This one closes 101 periodically. We are looking for long-term solutions for that, but some of these are so big that there just isn't really the kind of money that we need to do it. You know, California, where they seem to have a lot more money, they spent just last year on one slide alone $70 million, $70 million, yeah, $70 million, and they've done that almost every year for the last 20 years. We don't have $70 million, right? So basically they've spent $1 billion in a decade fixing landslides on 101, and frequently there's only like 100 people that live on the far side of them. Well, that's California. We're Oregon, we don't have that kind of dough. So in a lot of cases like Huskaneden, we just wind up living with them. That's probably the sexiest thing that we get to work on, and although it's depressing, I got to tell you, because you know, you're not really fixing them. Foundations, we drive steel pipe piles in the ground frequently, and in some cases, because we want a big, low excavation, particularly for bridge abutments and bridge bents, we have shoring. So you can see these steel H piles with wood lagging. That allows us to dig a hole that doesn't fall in on the workers. We've mucked out the bottom, and then we've driven these steel piles through there, and this person's cleaning up the bottom, getting ready to fill that with concrete and rebar. Again, that's Newburgh Dundee. This is a drilled shaft. This is a pretty interesting rig. That thing you can see hanging from the crane with all the little pointy bits at the bottom, well, it goes down through a casing, and those things rotate at high speed, and it will chew through anything. So it's a way that we make a hole in the ground in a drilled shaft. We then fill that with concrete and rebar, but we want to get through something to something good. In this case, on the side of the Sandy River, we got boulders that, you know, half the size of this room sitting over the top of bedrock. We got to get through those boulders. We got to get to something solid that we really want to put this bridge on rather than just setting it on a boulder. And so this rig right here, there's nothing that would stop it. It will just go and go and go. It's really expensive. You're not going to see that one very often. It's cool. We got a picture of it. But when you need it, you need it. And we would be the ones in our group to say, yeah, that's how we're going to get the drilled shafts in at Sandy River. This is our future org chart. Right now, Paul Wirfs will be up speaking after me. We report through Paul, through Susan Hopton up. But there's a change coming. There's currently going to be a hiring of a state geotechnical engineer that would report directly to Steve Cooley. And then down below here, you see the names of the various people who already exist. So Sean Rapp, who I talked about. Sophie Brown is in charge of retaining walls. Curran is the engineering geologist. I'm the geotechnical engineer. Susan Ortiz is the bridge engineer, so she works on bridge foundations and bridge seismic as well. And then we have some material source folks that you'll see in there as well. So this is our coming structure, which sometime this summer will be going forward. Then the real geotechnical work for projects is done in the regions. Each region has their own geotechnical staff. Generally, they have a senior geotechnical engineer and a senior engineering geologist, and then a series of other engineering geologists and engineers. The exception to that is Region 4 and 5, slightly less geotech work over there. So you have a senior geotech in Region 5 and a senior engineering geologist in Region 4, and they sort of split those services. So that's somewhat of a recent approach that we've taken to the east side of the mountains. So what guidance and tools do we have? We have a geotechnical design manual. Myself, Curran, Sophie, and Susan are predominantly responsible for working with the various practitioners in the state to come up with that document. It's your basic big, thick 3-ring binder. That's the main guidance that you have. That guidance then refers to AASHTO guidance that exists on terms of how to do foundation work and how to deal with geotechnical issues, FHWA guidance. A much lesser extent is the building code, but anytime we do anything that is in a city or a county where it's not just a bridge, then generally we would have to design in accordance with the building code. It happens. And then the Hazmat Program Procedures Guidebook, which is apparently currently under revision. I don't have any personal knowledge of that document, but these are the documents that we use to guide our work. Geotechnical deviation process, this is reasonably new. We haven't had it before. I'm sure you've heard of other deviation processes. So when a project element deviates from the GDM standards, then the region has to ask for a deviation from that. The professional of record, POR, completes an application. That could be an engineer or a geologist with the justification for why this needs to occur. A classic example would be we just can't drill as many borings as the guidance tells us that we need to, or we have this big liquefaction problem on this project, but there's no way we can fix that. It's just bigger than the entire project, and because it's not a lifeline route, we're going to let that go. Those kinds of things. It can take quite a bit of time to review, and sometimes there's negotiations. So far, I think we've had 2 submitted. Both actually went away, so I guess we're going to see how much time that takes. But ultimately, when it's obvious that a deviation is necessary, that just needs to be submitted as early as possible. This has only been in place for about 9 months, so we're kind of on the training wheels of it. So quality control, this is our big focus. If you've been around ODOT, you might have heard us talk about quality control. This is 2 projects that we're not proud of, but we're learning from. Pioneer to Eddyville is the one on the upper left. Our job is to make sure that once stuff touches soil, the soil stops moving. That's really our job. This is 2 cases where we didn't do that job. First one, Pioneer to Eddyville, you see these big bridge bents go in here, and the hillside is still moving laterally, even though the project team thought they'd stopped it. And they were wrong. And being wrong about that means that these fully built bridge bents are being demolished and pushed over on their sides and hauled off in a truck. And that's not an acceptable answer. And then the one on the lower right is Wickiup Junction, where we realize once in this case, the decks or the beams are already in, we find out that that's going to settle forever and is going to wind up 6 feet lower than we intended it to be. So that's the demolition of that structure. So these are 2 structures, 2 significant projects that were demolished because soil continues to want to move. So when those things happen, the focus is obviously on quality control. It has been in the past, but you just get this focus. So quality control is addressed in a new chapter of the GDM. We had various quality control manuals throughout the regions. We now have a statewide quality control manual. So we have a chapter within the GDM. One of the important things that it requires is that you have 2 reviewers on every project. So you have a senior geologist and a senior engineer who are not the professionals of record, who are reviewing the work of the professionals of record. So ultimately, you're going to have 4 professionals on every project. And it seems like overkill, but we know that if that occurs, neither of those 2 things happen, and we don't make those kind of mistakes going forward. So it's the single biggest change that we're making going forward. The reviewers are involved from the life of the project. They're at the kickoff meeting, and they're there all the way through construction. So it's not the old model, which was do a whole bunch of work, give it to a reviewer 2 days before the project is due to be finished, and hope that they like the work you did. That's not quality control, and we're committed to doing real quality control. Quality assurance, which is making sure that quality control occurred, that occurs after the project is complete. We have a new process for that as well. This is our list. Please memorize this of all of our deliverables and milestones. Every group within ODOT is really taking a hard look at these lists to say, okay, what has to get delivered when? And then we're looking at other folks' deliverables and saying, oh, wait, we can't get you that till then, but you need that here. And so ultimately, this process has kind of been negotiated out between a bunch of groups. And I feel like, we've done a good job, but that's our list there. Very huge interdisciplinary coordination. We provide recommendations to bridge and roadway designers, and hazmat can intersect with any of the disciplines and be involved in almost anything we do. The work is interactive, it's iterative. There has to be give and take between bridge engineers and roadway engineers and geotechs if we're going to do this job right. And we got to have communication between anybody doing design and our staff, or it's just not going to work. So what do? We're involved in any project that is constructed in or on the earth, which is basically any project. And the earlier you can start talking to us about the things that you're worried about, the earlier we can tell you why we're not worried about that or what we think the concerns are. Contacts, don't talk to me because it's Paul Werfs and Curran Money. So anybody can call me. In fact, I'm probably the most available of all those folks. I have fewer meetings than the rest of them, so feel free to contact me as well. And questions then, or are we going to do questions after Paul?